We've sketched how to type check the overall class structure and make sure that method overrides are consistent, but we still need to talk about type checking individual expressions. So we've got an expression to type, a list of all the typed class declarations. We also get the type for this because we need to be told from the outside. Like it depends on which method body we're looking at right now, for example. And we also need to be told the type of arg in case arg is used in this expression. It'll be handy to have a recur function to just call typecheckedexpr on some expression with the same last three arguments. In the case of an integer expression, then of course the type is just empty. If we have the word arg inside of method, then we were given as an argument here the type of arg, and the same for this. We're given this type. So those are all straightforward. Arithmetic is also pretty much the same as always. We have a plus or multiply with left and right. We make sure that left and right each have type integer, and if so, then overall we have type integer. And I've just written that as a local helper function here. The first interesting case is the new expression. For new, we have the name of the class that we're instantiating, and we have a list of expressions for the arguments to that new. Now those are expressions, so we will type check all of them, of course, and we can just use recur for that and map recur over all the expressions to get the actual argument types. And those arguments need to match up with the class's fields. So we're going to get a list of field types from that class. But we can't look at just the class declaration because some of the fields come from superclass or superclass maybe. So we'll have this helper function get all field types to get a list of all the field types in the right order. And then we will be able to compare these two things. As long as they have the same length and they don't have to be exactly the same types, right? Because if a field has type posin, we should be able to supply a posin 3D. So that's why we don't just compare these two lists directly. Instead, we make sure they have the right length. Then we map 2 over them to make sure that the actual arguments type is a subtype of the expected arguments, expected fields type. And this subtype needs a list of classes to do that. So here we get a list of booleans back, and then we just fold and over that list of booleans to make sure that they're all true. If they are all true, that means that our types that we're supplying for the fields are consistent with the class expectation. And what do we get back from new? We get an instance of this class. So our result type here should be obj with that class name. And if something doesn't match, well, then we can just complain with type error. In the case of get, we have an object expression and a field name. So the object expression is an expression. We type check it and make sure that it in fact does produce an object, not an integer. If it produces an object, then we also know what kind of object it produces. We get a class name back. And we need to make sure that this field name is in that class name. We can do that by looking for the field in the whole tree of class declarations. So again, the field might be in this class, or it might be in a superclass or a superclass, and so on. And it's the job of the find field and tree helper function to find the right one. And it's just going to return a type for that field because that's all we have in the class declaration, and that type is exactly the type of the fields that we get using the get expression. What if we call a method? We've got an expression and the method name and the argument for that method call. The object expression and argument are both expressions, so we recur to type check those. Then we need to make sure that to the left of the dot really is an object, and then we have a class name. We can look in this class for that method. Again, taking into superclasses and so on, but we'll defer that work to typecheck send. So typecheck send is going to handle method calls in general, where we tell it the class and the method name, the argument expression, the type of that expression, and the list of classes. And the reason we put this in typecheck send is, well, it's the same for a super. We need to do much of the same work. For a super, we got a method name and an argument expression. This class we can find by using the this type, right? So when you do super dot, it's kind of like using this dot, except you need the superclass type. So first we look up the class declaration based on this type, and then we can extract the superclass's name from that. And now, once again, we have a class name, a method name, argument, expression, and so on. So we can reuse our typecheck send helper function that we just sketched. To implement typecheck send, you find the method in the tree, either in the immediate class, the superclass, and so on. And if you find it, you got a method declaration with a declared argument type and a declared result type. So we can check whether the actual argument type that we got from this arg expression matches. And again, it doesn't have to be equal to the declared argument type, it just has to be a subtype of it. If it is consistent with the method's expected argument type, then we know the result type that the method declares. So we return that as the result of the method call. Otherwise, we complain about the argument mismatch.